Contours and level curves help us to understand the way that a 3D surface changes. A contour is a curve that traces the intersection of a surface and a plane. So these are essentially the traces that are parallel to the XY plane. A level curve takes that contour and projects it into the function's domain. Sometimes this is called a contour map. It's often that these two terms are interchanged and confused. So to help you remember, I'm going to bring up a makeup topic. So girls out there, when you do your makeup and you put a little bit of dark powder to make your jawline pop, that's like a contour, and you apply that to the actual face. So contours exist on the surface. Level curves, however, that's the projection into the function's domain. So let's say we have some surface in 3D, like the blue one you see on the screen. If I were to slice this with a bunch of planes parallel to the XY plane, like these red planes you see, and then map out the intersection of the surface and each plane, we see that represented by the green curves. Those green curves projected down into the function's domain would be the level curves. So when the curves are on top of the surface in 3 space, those are contours. But when they're squashed down and viewed in just the domain plane, that would be the level curve or the contour map. This idea is used often for topographical maps. Here I have 2 pictures of the Devil's Tower in Wyoming. Devil's Tower is this really cool rock formation, and it's very steep along the sides and then flat along the top. We can see that in the picture on the right, but we can also imagine it using the topographical map on the left. Notice that we've got different colors to help break up the different levels. Each one of these lines is mapping out a path of constant height on our 3D surface. So, for example, we see this pink circle in the center. This is representing that the top is flat. There's no more contours inside of this circle, and that is showing us that we're flat right on top. And then as we move away from that, we can see multiple curves, and that's showing you that each one of those curves is at a different height. Multiple curves are showing you that the side is decreasing or changing in height. In this case, it is decreasing. Yosemite Valley, right in our backyard, is another great example of a topographical map. Notice that the valley is very low elevation, and all along the edges we have these steep cliffs. We can see the steep cliffs in our topographical map as multiple contours right next to each other. So these level curves in the contour map are very close together, which represent a quick change in elevation. In spaces where you don't see any kind of multiple curves next to each other, you can assume that's like a meadow or a flat spot, because everything within that pretty green area is at the same height, so it's not changing height. Anybody who goes on to study oceans or even the planet might see pictures like this where it's not actually representing height, so to speak, but it's trying to break up functions' outputs into different categories. So here we're looking at the potential temperature of the world. In this case, potential temperature is not like potential energy. Google it if you want to know more about it. But potential temperature on this map, we can see that the Earth is warmer towards the equator. We can tell by comparing the colors that we see along the center portion of our graph and the colors that we see on our key or the legend. So in that center part, we can see most of the temperatures are about 27 degrees Celsius. And then as we move towards the poles, the temperature decreases to about 0 degrees Celsius. And we can see that there are pockets of somewhat constant temperatures from the equator as we move out towards the poles. So these contour maps, level curves and contours in general, they're really useful for breaking up portions of a function that are alike. So when you want to represent a function by grouping the similar outputs, we can use these level curves or contour maps. We looked at the function g of xy equals the square root of 9 minus x squared minus y squared earlier, and we actually created our level curves or our contours by hand. We took the function, set it equal to a constant, and solved, and we found a bunch of circles centered at the origin. The largest circle was in the xy plane, and as we allowed z, or the constant that we set our function equal to, as we allowed that to increase, our circle's radius shrank until it finally landed on a single point. So we have a contour at the constant 0. We had a contour at the constant 1, a contour at the constant 2, and a contour at the constant 3. And each one of those can be projected into the domain. And we can see the 3 circles and the point is right here, of each one of our contours projected down into the domain for our contour map or the level curves. Now earlier we went through how to find each one of these circles. So if you're curious about how to find the level curves that correspond to these different c values, go back to the traces of multivariable functions video and you can watch how to do that there. Let's take a look at a new function though. Here we're looking at the function f of xy is equal to y squared minus x squared. And if we want to find some level curves for this function, maybe the first thing we do is set our function equal to some generic constant, like k. And then we ask ourselves, if we were to change k to different values, how would that function change? How would that map change? Well, if k is equal to 1, this just looks like a hyperbola. If k is equal to 2, we could make it look like a hyperbola simply by dividing the entire equation by 2. Same for k equals 3. If we divide the entire equation by 3, we would get another hyperbola. And so on. If we were to map these out on our surface, in the xy plane, our hyperbola would trace out, oops, I'm drawing that in the wrong direction. These are opening on the y. So we have hyperbola here, and a hyperbola here. And then as we go up, our hyperbolas are moving away from the z-axis, and they're contracting. So when we go to graph our level curves, let's do these in different colors to really make them pop. So this is just a sketch. We're not doing a perfect graph here. But if we were to let k equal 0, then we would get this set of hyperbolas. As k increases, the hyperbola is moving away from the origin and it's also contracting. Let's take a look at another function here. The square root of of 8 plus 8x minus 4y minus 4x squared minus y squared. We want to create a contour map for this function. But first, let's start by finding the level curve that corresponds to c equals 0. So that means we're going to take our function and set it equal to 0. And we're going to try to work this until it's something that we can recognize. So maybe we square both sides to get rid of our square root. And as it's written, we might not recognize this surface, but we have some algebra tools that can help us here, like completing the square. I'm going to take the two terms that involve x and complete the square in x. So if I have a negative 4x squared plus 8x, the first thing I'll do is factor off the coefficient, negative 4. And then I'm going to complete the square inside of the parentheses here, just to make things easier. Completing the square uses the b divided by 2 squared, added and subtracted. So we'll have 2 over 2 squared. So we are going to add 1 and we're going to subtract 1. Doing that will allow us to complete the square in the first 3 terms. So x squared minus 2x plus 1 factors to x minus 1 squared. And there's a relationship between this b divided by 2. Oh, I should have a minus. Nope, I shouldn't. I should have a minus right here. Negative 2 divided by 2 would give us negative 1 squared. That b over 2 term is exactly what shows up in that factored form. So if that sounded a little bit head spinning, maybe it's time to review completing the square. But the point here is to complete the square in x so that we can recognize the equation we're working with. So we have minus 4x minus 1 squared, and then I have another minus 1. I'll distribute my minus 4 to each term. So now, instead of 8x and negative 4x squared, I'm going to replace just those two terms with these two terms. And now I want to repeat this process, but I'm going to complete the square in y. I'll pull out any terms that involve the variable y, and we'll repeat the process of completing the square. Oops. So we have minus 4y, and we also have minus y squared. Now in this case, I'm going to factor out a negative, because the easiest way to complete the square is to have a positive 1 coefficient on the leading term, on the quadratic term. So to factor out the negative, I achieve that goal. And then we're going to complete the square inside of our parentheses. So I take the b, cut it in half, and square it. That would be 4 over 2 squared, or 2 squared, which is 4. So I'm going to add and subtract 4 so that I can complete the square in the first 3 terms. Y squared plus 4y plus 4, that turns into y plus 2 quantity squared. Bring down the rest. Distribute my negative back in. I'm going to replace the y terms that we had with the completed square version. Now all of that is going to allow us to rewrite this equation where we've grouped together all of the x terms, grouped together all of the y terms. It'll be much easier to work with this version of our equation. I've got some constants that I'd like to combine. I have 8 plus 4 plus 4, so we've got 0 equals 16. And then minus the two factored terms, so minus y plus 2 squared minus 4 times x minus 2 squared. If I add those two binomials to both sides of my equation, I can see that I have a circle centered at x equals 2, y equals negative 2, and we have a radius of 4. So the level curve that corresponds to c equals 2, it gave us a circle centered at 2, negative 2 with a radius 4. We can repeat this process. Instead of putting 0 equal to our function, we could have put c equal to our function. So that would look like c equals, I'm going to pick up from right here because that's the factored version. I like that a lot better. That would be 16 minus y plus 2 squared. Actually, I'm going to move those binomials to the other side so that we have positive terms. So we'd have y plus 2 squared minus 4 times x minus 2 squared. Replacing the zeros with c's would just mean that over here on the 16 we'd have minus c. So as c increases, the radius shrinks. We know that we're not changing the center of our circles, we're just changing the radius. So when we go to make our contour map, we're making circles that are centered at x equals 2, y equals negative 2. The largest circle had a radius of 4. And as c got smaller, the circles get smaller. So that would be our contour map. The domain for this function would make sure that the argument of the radical is 0 or larger. So we could take that input, set it equal to 0, and find the values that work for the domain, and then we could find the corresponding range of our function. We've already done examples like this, so refer back to the previous videos to see how that's done.